Hello everybody! In this video I present a strategy to tune single can test rigs in order to use them to explore the thermoacoustic properties of a full can-annular combustor. The work was done by me and co-workers at TU Munich, and the corresponding paper is published at ASME Turbo Expo 2020 under that paper number. Imagine the following situation. We are in the late design phase of a new can-annular combustor, and before we put the combustor in operation we want to do an extensive test campaign. However, building a full-scale test rig is typically too expensive, so we typically study the performance of the combustor with a single can test rig, as shown here. This test rig comprises one can and the corresponding sector of the compressor exit plenum here and the transition piece towards the first turbine stage here, also called annular gap. It is well known that with such test rigs we can test local phenomena like emission levels or flame stability. However, the question that we want to address here is, can we also use our single can test rig to explore the thermoacoustic properties of the full combustor, which is also a very important point to address in this development stage. To answer that question, let's look at the problem on a schematic level. In the full can-annular combustor, the individual cans are coupled acoustically via the compressor exit plenum and the annular gap in front of the turbine. This gives rise to azimuthal modes that extend over the entire circumference of the combustor and involve all the cans simultaneously. In our single can test rig, however, this coupling is not present. Therefore, these azimuthal modes are not represented, except the axial mode with the azimuthal mode order m equals 0. Thus, the answer is no, we cannot directly use single can test rigs for investigating thermoacoustics of the full engine. The question addressed in our study is now, can we somehow tune the test rig to still use it for thermoacoustic investigations? To answer this new question, let's first consider some theory. Typical can-annular combustors feature a discrete rotational symmetry. According to Bloch-wave theory, which was originally developed by Bloch in 1929 and which was first applied in the thermoacoustic context by Mensa et al. In 2016, the full combustor can be represented by one single sector, while at the cutting interfaces here, so-called Bloch boundary conditions are applied. Now if we compare this to our single can test rig, except those Bloch boundary conditions here, the full engine is actually identical to our single can test rig. We now define some equivalent reflection coefficients at the in and outlet terminations of the single can, so in the full engine and in our test rig, and we know that if and only if these reflection coefficients defined here at the in and the outlet of the can are identical in the full engine and in the test rig, both systems will show identical thermoacoustic properties. We therefore have to somehow tune the terminations of the single can test rig in order to mimic the effect of those Bloch boundary conditions here. In the present study, we investigate the capabilities of passive acoustic elements to do this tuning, namely duct extensions and Helmholtz resonators. Those are used to match these equivalent reflection coefficients of the full engine and the single can test rig. In the rest of the talk, I will first present a strategy for tuning the mentioned passive acoustic elements in order to match the equivalent reflection coefficients. Afterwards, we apply this strategy to a numerical model of a representative can-annular configuration. And in the last part, a short conclusion is drawn. Let's come to the adaption strategy now. Before we can match those equivalent reflection coefficients, we obviously have to compute them first. So this is the first step of the adaption strategy. To do so, the can has to be cut away from the plenum and the annular gap at appropriate locations here. The plenum and the annular gap are then modeled numerically, for example by means of the Helmholtz equation. The equivalent reflection coefficients are now computed by forced response of these cutaway elements. There, it is important to note that Bloch boundary conditions have to be applied at the azimuthal cutting interfaces of plenum and azimuthal and annular gap. Here you see the resulting equivalent reflection coefficient for an exemplary setup, and the gain of these equivalent reflection coefficients depends only of the gain of the terminations towards turbine and compressor, and it's therefore not shown. The phase, however, depends non-trivially on the frequency and is shown in the plot. What is important to note here, due to the Bloch boundary conditions here, we get individual reflection coefficients for each mode order m. N here is the total number of cans, so in total we get n half plus 1 individual reflection coefficients. Now, after we know the reflection coefficient, the next step is to fit the passive elements to match this reflection coefficient. As already said, we investigate two types of elements, Helmholtz resonators and straight duct extensions. The corresponding reflection coefficients of these elements are shown in the left plot, together with the equivalent reflection coefficient Rm of one single mode order. In general, the reflection coefficients will only match at one distinct frequency f0. This is therefore called the design frequency of these elements. As we cannot match the reflection coefficients for the entire frequency range here, the reflection coefficients at least have to match at the dominant frequency of the full engine at the investigated mode order m. So only if the design frequency is equal to this dominant frequency, the test rig will show the same thermoacoustic properties. However, this dominant frequency of the full engine is not known a priori. We may only provide a good initial guess by, for example, taking the dominant frequency of the previous mode order or that of the axial mode m equals 0, which can be measured in the unmodified test rig. We therefore propose an iterative adaption process where the test rig is successively operated, its dominant frequency is measured, and the tuning elements are adapted or redesigned accordingly. As shown in our paper, this process ensures that the dominant frequency of the test rig converges to the dominant frequency of the full engine at the considered mode order m. After this convergency is reached, the stability properties of the tuned test rig and the full engine will be also identical, and the test rig therefore represents the thermoacoustic behavior of the full engine at this particular mode order. This was the procedure for one single azimuthal mode order. These steps are now repeated for all remaining mode orders of the full engine. In this way, we can successively explore the thermoacoustic properties of the individual mode orders of the full engine using this tuned single can test rig. Our study revealed that Helmholtz resonators are actually better suited for test rig tuning. As you can see in the plot, the reflection coefficients can be well matched in a large range around the design frequency f0. This makes it possible to investigate entire operating windows with possibly changing dominant frequencies without the need of redesigning the elements. Additionally, its design parameters like the neck length or the neck area ratio should be remotely accessible, which is actually a huge advantage in a high pressure test rig. Last but not least, the finally obtained resonator geometry is expected to fit in existing high pressure cells. On the other hand, the duct extension lacks all these advantages and is thus considered to be not practical. Thus, in the following case study, we will only consider Helmholtz resonators for test rig tuning. The proposed strategy is now applied to a numerical model of a representative can-annular combustor. The case is modeled using 3D inhomogeneous Helmholtz equation, and the flame response is modeled with an FTF multiplied by a generic saturation model. The FTF and the saturation model are taken from those two studies here. The equivalent reflection coefficients are defined at the locations here and here. The plot on the left shows this equivalent reflection coefficients of plenum and annular gap, and for the annular gap here, the various mode orders are quite distinct from each other, while for the plenum they are very close together. This is due to the huge area change between can and plenum, which essentially decouples can and plenum. This indicates that can-can coupling via the plenum is relatively unimportant. We confirmed this in the paper by simulating the identical setup while removing Bloch boundary conditions here at the plenum. This essentially suppresses any coupling via the plenum. The resulting limit cycle frequency and amplitudes for this downstream only coupled case are less than 5% different from the fully coupled reference case. Thus, we can apply the adaption strategy only on the downstream side without significant loss of accuracy. This slide now shows the result of the adaption with Helmholtz resonators at the downstream side, exemplarily shown for mode orders 1 and 8. For both mode orders, the Helmholtz resonator can be designed to match the equivalent reflection coefficient very well in the wide frequency range. Therefore, we need at maximum only one iteration to fit the resonator. For m equals 8, we do not even need any iteration, and the resonator actually converges with its initial design. Compared to the full engine, the adapted test rig shows limit cycle frequencies with a relative error smaller than 1% and limit cycle amplitudes with a relative error smaller than 5%, which is considered as a quite good accuracy. With this slide, I want to conclude my talk. So we proposed a strategy to adapt general passive acoustic elements for tuning single can test rigs acoustically, and we showed that Helmholtz resonators are actually a very good candidate for this test rig tuning. The strategy was then applied to a numerical model of a representative can-annular configuration. There we could show that can-can coupling via the plenum is relatively weak and might be neglected. Finally, we proved that our adaptation strategy is working with good accuracy, and it's also efficient. However, this was only shown in the study with numerical models, while the strategy is actually intended to be applied in an experimental test rig. Therefore, experimental validation of the strategy is still missing. Thank you for your attention, and read the paper.